Okay, we are live now. Hello? On mine?
Yeah, I'm here.
Okay. So, hello everyone. Here is CrossDvlup from Madrid with his first live meeting. So let's start with Tanmay from Hasura.io about architecture of scalable and resilient Node.js app with GraphQL and event-driven serverless. Okay. Any question I will be reading. So some question I will stop Tanmay and let's do this answer. Okay. Thank you, Tanmay.
Absolutely. Thank you. Thank you for the introduction, and thank you everyone for having me. Super happy to be a part of the first live meetup at CrossDvlup. So I'm going to talk a little bit about an architecture pattern for building resilient and scalable backends with event-driven serverless and GraphQL, and a pattern that works, and kind of showing you a few examples of how that can work for Node.js. So just before I get started, quick introduction. I'm Tanmay. I'm one of the creators of the Hasura open source project, and now the founder of the company behind the project as well. And this is an open source project that gives you real-time GraphQL and eventing for serverless on top of Postgres. And eventually we'll kind of be supporting other databases as well. You can check this out at Hasura.io. The architecture pattern that I'll be talking about today is called three-factor. We call it the three-factor architecture, and you can kind of read about it in a little more detail at threefactor.app. And there's a kind of a discussion there about what kind of different tools you can use for setting up this architecture and stuff like that. So you should definitely check that out as well. To give you a little bit of background about my background, I did my bachelor's and master's in computer science a while back, and after that, I did. I in fact did it with I did my master's in machine learning and computer vision, and I did a little bit of consulting for a few research labs. After that, after which my team today that I work with, we started working. We started doing consulting for enterprises and for startups, where we would build products and we would help them migrate to kind of microservices, from monoliths or start containerizing their workloads. And we were very early adopters in the Kubernetes and Docker ecosystem. We did all of the wrong things imaginable with Docker, like having multiple services inside a single Docker container, because none of these patterns were figured out, just around the time when it was hitting 1.0. And similarly, we were fairly early adopters in the Kubernetes ecosystem as well. We had worked closely with the team there, found a few interesting bugs, did a few minor contributions upstream, and kind of was exciting to be a part of that journey. And soon after that, just about a year and a half ago, we started Hasura, which is where we a lot of the technology that we were working together, that we were working on, came together as a part of this open source offer that we have now. So that's kind of my background. And over the last year or so, I've been fairly excited about the GraphQL and serverless ecosystem, and that's kind of the background that I'll be talking to you from. So let's kind of start off with describing the problem that we're attacking. So if you look at a traditional architecture for an application that you're building, right? Let's say you're building an e-commerce food delivery app, and so what you do is you typically have an app. And this is a mobile or a web app or an Android app or whatever, and you have an API layer that you write, and this API layer will kind of talk to the app with APIs, of course. And this API layer itself on the back end will talk to a database. It will talk to different microservices. So maybe if it's an e-commerce, or in the example that I'm going to take, like a food delivery app, it'll talk to a payment microservice, or might talk to a restaurant microservice, or a delivery microservice. This might be a monolith. It might be multiple microservices. It might be just one microservice. But after a certain point of time, this is kind of what your application will start might look like with microservices. One of the when we kind of start off with this architecture, right? The reason from moving to, let's say, not having built this whole thing as a monolith, and instead of that kind of migrating towards a microservice, the main goal towards moving towards microservice was that we kind of independently encapsulate logic for different domains in our business context, and we can work on them independently. We can iterate on them independently. The ownership is independent, and the scalability is also independent, right? And that was the desire of moving from microservices to monoliths. But if you look at implementing microservices in this style, this does have a few problems, right? For example, if you think about it, when you think about scalability, you have to when you scale the API layer, right? It actually depends on the scalability of the individual kind of microservices that you're talking to. So scalability is not necessarily independent, especially if you have an API kind of front layer, right? If you think about resiliency, where you want to be tolerant to failures that might happen, in just implementing microservices in this style, it might be hard for you to get resiliency. Let's take a particular example. Let's say our API, does something on the database, and after doing something on the database, the API talks to a microservice. Now, let's say the microservice returns an error. So if the microservice returns an error, you need to kind of do a rollback on the database, or you need to handle that error, right? And when you have multiple microservices, anything can happen. Let's say we were talking to database, microservice 1, microservice 2, microservice 3. Let's say microservice 2 failed. Do we roll back microservice 1? How do we communicate the error back to microservice 1, right? What if the failure that we got from microservice 2 was not actually a failure, but it was a transient network failure, where actually microservice 2 succeeded in the API call, but we couldn't capture the response effectively, right? And so now, how do you handle that error? And you can, of course, and it kind of starts becoming painful to handle these kinds of transient failures that you can have when your microservices are directly dependent on each other, right? Also, it's 2019, and microservices are just boring and old now. So it's time to move to something else. Just kind of a joke there. So if you kind of take this microservices architecture and you want to start thinking about making it more scalable and resilient, what you'll start doing is you'll say, what, let's make everything asynchronous, because anyway these network calls are asynchronous, right? Why don't we have a fundamentally asynchronous architecture, right? So in that approach, what you would do is you would kind of try to move towards an architecture where your app communicates to an API layer, which will communicate maybe synchronously or transactionally to some kind of a data system, which then has an event system closely associated with the API or with state changes in the database, however you architect that system. And events will be emitted in your kind of business domain. And those events will trigger microservices, or will call out to microservices, or will be delivered to microservices asynchronously. And so you will deliver it to the payment processing microservice, which may or may not go and update the same database, or may update a different database. It will have some kind of state change. Then once that event succeeds, the next event will be triggered for the next process in your workflow. So if you're looking at a food delivery application, after you do the payment, now you have to check if the you might want to check if the restaurant or the restaurant has approved this order, right? Their order is actually going to be delivered. And after that, once the restaurant has approved it, you assign a delivery person, run some complex business logic, find out who's close, what delivery person is close by, match the ratings. A 4-star client will get a 4-star delivery person, stuff like that. And that will be the next event. And you will trigger all of these things via an event system instead of the API directly talking to the microservices. The reason why this is useful is because now everything is captured inside your event system, right? And that means that, if something goes wrong, if there's a network failure, all you have to do is redeliver the event from the event system, because the event system is a persistent log of the events that have happened. And that makes it easy to think about, how will we handle failure? It also makes it easy to think about scalability, because now scaling the API layer is completely independent of scaling these microservices, right? The microservices that have to scale have to handle the load from the event system. And the API that has to scale has to just deliver events into the event system, or just has to make state changes in the database to make those state changes, right? So it's much easier to reason about the scalability and to reason about the failure tolerance of your microservices. So that's the architecture that most people kind of end up moving towards after starting off with a base microservices architecture, right? And again, I just want to be clear that the API layer that the app is talking to is kind of the API layer that is creating the events, or that is doing synchronous, doing synchronous actions, actions that cannot be asynchronous, because sometimes you have actions in your application that cannot be done asynchronously, or doing them asynchronously is just unnecessarily hard. And that kind of synchronous logic goes into the API. But the async logic that you have in different microservices, can be delivered or can be fulfilled by different microservices. So that's kind of what an async architecture starts looking like. One of the ideal candidates for implementing asynchronous kind of functionality is serverless. And so let's kind of take a quick look at serverless. I'm sure most of you have heard of serverless, and I'll kind of try to put serverless into context of why it's a really great fit in this architecture. So if you do serverless, the experience of writing serverless is basically that you do a function that handles a particular API call. So in this case, I have a API handler that will return hello world, right? And then what you do is you just deploy that function to your provider. So this is just a placeholder kind of code snippet. This could be AWS, this could be Google Cloud, this could be Zeit. You have a bunch of different kind of tooling to help you deploy the serverless function to a serverless provider. And then when you do that, what you get is you get an API endpoint, or you get an HTTP endpoint on which you can call this serverless function. And then you can kind of just use a web client or a browser or whatever to make a call to that HTTP API, and you will get a response from that particular function, right? So so that's kind of the experience of building with serverless. If you look at this, and in this experience, which is I've kind of simplified the commands, you don't actually have to deal with anything else, right? As a developer, this is all that you deal with, right? You write your code, you deploy your code. It's a restricted environment. You can't do all the things that you would have done on your own laptop or in your own dev machine. It's a restricted environment, but the work that you do is kind of scoped into just doing this. This is also scalable because we are not managing how the serverless function runs, right? So as a developer or as a team that is kind of building business logic in the serverless style, you're writing code and you're deploying it, but you're not doing any operational work. Or I won't say any operational work. That's a little bit of a lie. You're not doing too much operational work, right? You're not actually creating a VM, and you're not going to the VM and kind of saying that, provision this VM, create a, install the Node.js runtime on the VM, and then install dependencies if you need to install those dependencies, and then kind of run my function, right? You're not thinking about your work from that VM kind of standpoint, or a server standpoint, which is why the name serverless kind of comes in. Because of not having VM managed, you don't actually have to worry about scaling. So let's say, for example, you have a spike in traffic. So then you need to worry about, all right, so I have a VM. My VM has 512 MB of RAM or 1 GB of RAM, and it has 1 core or 2 cores or 3 cores, right? And especially with Node.js, leveraging multi-cores, a multi-core environment is a little bit harder than what you would do with, say, PHP or Haskell or something else. You would have to use some kind of a clustering or processing or a process clustering module that will help you leverage multi-cores easily, right? So you need to now think about, okay, what kind of VM do I create? How do I exploit multiple cores to kind of efficiently use the VM? And then have to monitor the VM, because if I get a sudden spike in traffic, or as traffic increases, we need to keep a track of what is happening on the VM to see what the RAM and CPU and IO consumption is. And if that crosses a certain threshold, we'll scale it out. And it's becoming easier to kind of scale out and do auto scaling with VMs and whatnot, but you still actually have to monitor and worry about it, right? With serverless, the idea is that you write the code, you deploy it, and you scale for quote unquote free. So there is no such thing in the world as scaling for free, but it is an illusion to scale for free, right? So you're saying that, okay, I can write my code, and this is what actually the, whatever we discussed that we are doing manually in the VM world is actually what the cloud vendor is now doing for us. It's not actually serverless. It's not actually not running a VM. It's not magic, right? So when you take the function and you deploy it, what's happening is that the cloud vendor says, all right, this is a Node.js runtime. In the Node.js runtime, this is the module or the code that we want to run. And this is the main function or the entry point function. And if there is an HTTP API event, we will call this function. So now every time you make an API call, what the cloud vendor does is that the cloud vendor actually provisions a container or provisions resources for you to run this Node.js code. So when we call the HTTP API, what will happen is that the cloud vendor will kind of, create resources and provision resources for a 512 MB RAM or a 1 gig RAM kind of environment. It will give you a CPU and it will take your code, it will run it there. And once your code runs and your code exits, the cloud vendor will actually deprovision or free up the resources, right? And when you have 1,000 API calls, the cloud vendor will automatically spawn 1,000 instances of your function, right? And if you have 2, it will automatically spawn 2. And if you have 0, the cloud vendor will actually not spawn anything for you, right? There'll be no resources provisioned, and you will actually not be billed for it as well, right? So in a sense, this is kind of freedom from ops, right? Like the operational issues with thinking about scaling is kind of reduced because you only have to think about what is the resource consumption that I will need for one instance of this function. And if you know what the resource consumption for one instance of the function looks like, you don't have to care about anything else, right? And this is kind of the environment that serverless tries to give to you, right? This is also quite awesome when you think about the serverless functions. It's interesting because when you think about your team, right, that is building features, what you can start doing with serverless is it's kind of like an extreme version of microservices, right? It's as if when in microservices the ownership was of a service. In the serverless function, what's happening is that the ownership is of a particular functionality, right? When you're deploying with Lambda, let's say, your ownership of the code that you're writing depends only on a particular function, right? This is both good and bad. This means that, for example, if you want to iterate on the logic of a particular function, a particular developer or a particular team it's hyper modularized, right? They can iterate on just the logic of that module and not worry about anything else, right? You don't have to redeploy any other service. You don't even have to talk to other members in your team who have built other functions. You just have to iterate on your own function and deploy it, right? And that is nice because you have complete ownership, end-to-end ownership of the business logic that you write, even at an individual level, right? Not just at a team level, which you got with microservices, but even at an individual level, you can say, you know what, I own these functions, and if anything needs to be done with these functions, I will redeploy them, I will test them, and I will take care of them end to end, right? And that is an amazing experience for a team as the team itself scales out, right? So it's not just scalable. It's not just a scalable approach to writing code, but it's also perhaps a scalable approach of working with a team. Now, of course, all of these comes with caveats. So none of this is 100% true. And there are cases when this will not always be true. But this is one of the ideas or the promises behind working with serverless. The other cool thing, if you think about serverless, is that serverless is event driven, which means that when an event happens, the cloud vendor will trigger a serverless function, right? As opposed to a microservice where the microservice runs, you provision resources, and the microservice is running 24/7, and then you can kind of auto scale the microservice, so it's 1 to n. Whereas in a serverless environment, it's 0 to n. Right? It's not 1 to n auto scaling, it's 0 to n auto scaling. That means that whenever an event happens, like an API event, or whenever your cloud vendor might give you other events, right? So on AWS, you might have an S3 bucket is created event, or something is uploaded event, right? On Google Cloud, you might have Google PubSub. There is an event in PubSub, and that event is triggering your serverless function, right? So different events are given to you by different cloud vendors, but in the most common case, we'll take the HTTP event. So whenever there's an API call event, the cloud vendor actually triggers the function for you by actually provisioning resource and running it for you. When you couple this idea with an event-driven system, like let's say your backend itself is event-driven, this kind of idea becomes nice because you are now forcing yourself to think about your architecture in a way that the functions that you're writing are ephemeral, which means that they will kind of spawn up, they will run, and then they will die, right? And that means that you can't have any state inside your serverless function. You can't actually have a global variable. You can't have like a request counter inside your serverless function. So you can't say that every time there's an API call, we'll increase a global variable called a counter, right? And so now for every 10 API calls, our global counter variable will go up by 10. You can't maintain that state, right? And that's painful, but that's also nice because every time you create more state in your application, that is state that you have to worry about. And when you think about scaling, that's the kind of state that doesn't scale, right? For example, if you implemented a request counter by having a global variable, you just fundamentally cannot do that with serverless. But that's also something that you should not have done with microservices, right? Because if you wanted to horizontally scale it out, obviously a global variable that is holding state will not work, right? Again, I'm sure nobody's actually keeping these global variables, but I'm just saying that it's not even something that you can do with serverless, right? And that kind of forces you to start making your application more and more stateless. And so every time you want to handle state, you can't do it inside the serverless function. You have to delegate it to a database. You have to delegate it to some kind of object storage with S3. You can't handle the state yourself in the serverless function, right? You can't save to disk yourself. There's no notion of whenever an API call comes, the serverless function will save it to disk, and then the next time the serverless function runs, it will read from disk. You cannot do any of that, which is interesting. And the way you think about serverless function is that you're triggering them on events, right? So what you do is, if you think about events, you can add retries to the events that are being delivered, right? And this automatically becomes one step to failure handling, right? So let's say you ran a serverless function, did not run successfully. You can, just by adding retries, you can start preventing certain kinds of transient failures, right? You can have a finite number of retries. You can have an exponential backoff where you do one retry and the serverless function responds saying, try again after 10 seconds. And then you try again after 10 seconds and the serverless function responds to try again after 20 seconds, right? So you can implement your own exponential backoff, which is great when you are using APIs that themselves might be limiting, right? So it kind of allows you to start building in failure handling logic in a way that you would have had to do anyway if you were doing if you were working with microservices or you were working with multiple API calls, right? And that kind of approach to having events, to being able to deliver events when you want them to, either by retry logic or by manually triggering redeliveries, you can start building in resiliency from the ground up in your application, right? You don't have to think about resiliency as something that you have to do later on. It's something that's naturally a part of your system because of the architecture that you're writing, right? So let's take a food application, for example, right? So every time we get whenever we place an order, let's say this is the object that gets created in the backend, right? We have the notion of a food delivery object, which has an ID, which is created by a particular user at a particular time, and which goes through various state changes, right? So the order is validated, the order is then going through a payment process, the order goes through an approval process, and then you assign a delivery person, right? And these are the various state changes that can happen to a particular order object. And every particular state change is driven by some business logic that runs your serverless function, right? And every time a state change happens, it can trigger the next event, which might trigger the next serverless function, right? So this is kind of what your state machine might look like, right? You have a new order that is created where nothing is validated or paid or approved or no delivery person is assigned. You run one serverless function which takes you from that and does your order validation. So your order is now validated, so it's ready. So this is a valid order placed by the user. Whatever you want to check, whether the menu items are valid, the food items are valid, stuff like that, or whether the restaurant is open, for the order to be placed, stuff like that. Then once that validation process happens, you do check. So you check if the payment is done, you check if the user has credit account, the user can make however they need to make the payment, and that triggers the next state change. Right? Once that state change happens, you trigger you are triggering the approval process for the restaurant. Right? This can be a manual process, it can be an API call, or it can be some business logic that you're running in a Lambda, right? And so on till you actually assign the delivery person for processing this order. So now you're thinking of your application as a state machine, where state is gradually changing, and every time the state changes, the state change is done by a serverless function, and the state change triggers an event for the next serverless function. Excuse me. So, and so that's kind of how we're taking a new order, a processed order, right? So that is kind of what one pipeline can possibly look like, right? So the cost of building, right? So the cost of moving to this architecture, like this architecture kind of sounds great on paper, but there is a cost associated with kind of moving to this architecture, right? And let's kind of understand a little bit what that cost is. So first, this works well if you have a generic event system. Sorry, folks, let me just turn off my notifications. Right. So the cost of the system is that you need a generic event delivery system, right? The whole idea was that we are taking away the work that we are doing in our business logic to do resiliency and to do scalability. We are taking away all of that code at some level, and we are pushing it inside the event system, right? So we need some kind of an event queue or an event system or event generation that is failure resistant, that will persist, that will scale, right? So we need that generic component, and we need to set that up. So that is the cost of moving to this architecture, right? And the other cost, of course, is that you have to rethink a little bit the way that you're writing code to be kind of like async on the serverless side, right? And it can also be synchronous on the serverless side, in which case it will go into the API layer. So you can have synchronous serverless functions here, and you'll have asynchronous serverless functions here, right? That's what this this looks like. One of the things to kind of look at here is that if you that there is a bit of a change to your CI/CD, to the way you're thinking about code when you start moving to serverless, right? The move from just moving from microservice to serverless is not super. So so again, if we kind of this is what we had before, and this is what we are kind of moving to, right? Where you have where you're taking your synchronous logic and you're making it asynchronous, right? So this is the high-level transition that we are kind of making in our thought process and the way that we're thinking about the back end of our application, right? So this on paper still sounds nice, but there is one key problem that we haven't talked about, right? And the key problem is that whenever stuff happens asynchronously on the back end, ultimately the mobile or web app that needs to be able to consume information asynchronously, right? It's great to say that stuff will happen asynchronously on the back end. That we have an order object, the order object has changed, and now the order object is ready for payment, or the order object is ready for delivery, right? That changes happen on the back end. How do we get that change on the front end to actually show it to the user? Because ultimately, it's that kind of user experience that we need to give to the user that has to be similar. And this is one of the key reasons behind why we don't do stuff asynchronously, right? One of the big reasons behind it's so easy to just write one API that will do all the 3-4 things and then return that information back to the app, because it's so simple to build the app. The mobile app has to make one API call. It will wait for the result of that API call, and the API call will have all the results, right? We don't have to consume a series of events on the front end, or we don't have to somehow get asynchronous information from the back end to the front end, right? And this is a problem. This has always been a problem when you're building asynchronous backends, because getting that information on the front end is a challenge, right? So, and this is where GraphQL is a wonderful fit for solving. So let's say, for example, that this is the data that is changing in our Postgres table, right? We have an order object, and the order object, you can see in the GIF, is going through asynchronous changes on the state. It's somehow changing. We don't care how it's changing. It's changing because of some serverless function that is running, and the payment status changes to true, the dispatch status changes to true, and these changes happen. What we want to do is reflect these asynchronous state changes on the front end, right? What we want is that when the payment changes to true, we want a UI that shows, hey, payment is done, or we want the UI that shows, hey, delivery is done, right? So whatever kind of UI we're building, maybe we don't have multi-stage loaders, maybe we have one loader which waits for all of the state changes to happen. Whatever that design is. But this is the async information that needs to flow from the back end to the front end magically, right? In a failure-resistant way, because we have to remember that mobile and web apps cannot keep a connection open for a long time, right? Your network connection might go off and on. Your network connection might be slow. The user might turn off entirely and reboot his or her phone. So all kinds of things can happen, right? With GraphQL, that experience is made easy, right? So I don't want to go into the details of what GraphQL is and how it works, but the idea behind GraphQL is that GraphQL is like a spec, just like how REST was a spec that you can do get, post, put, patch, delete. GraphQL is a spec that says clients can do queries and mutations to the server, right? So it's just another way of talking to your API. And the good thing about GraphQL is that there are standardized GraphQL clients, just like we had standardized HTTP clients. But the problem with HTTP clients was we never had a really good standardized REST client, right? Because REST was so flexible that you could do anything. So that is why you did not have a very standard REST client, but you have very good HTTP clients. So a GraphQL client is basically a wrapper on an HTTP client which knows how to talk to a GraphQL server. And you have client implementations for all of your major front-end platforms and frameworks, right, which the community is building. The cool thing that the GraphQL spec has, apart from being able to read data or write data, and that comes with its own advantages with GraphQL. But the key aspect of GraphQL that is important to us in this discussion is that GraphQL has support for subscriptions, right? It's almost as if you can imagine that the REST spec had get, post, put, patch, delete, and also had watch. So imagine if your REST kind of spec had a verb to watch data, right? So if something changed on that endpoint, you would automatically get information from the backend, over WebSockets or whatever, which are now a part of the HTTP spec, but people don't use them. Is that you will get that information asynchronously from the backend to the front end, right? And that's kind of the experience that GraphQL subscriptions give you, where you don't have to write WebSockets code on the front end. You just have to use a GraphQL client and you can use a subscription. So let's see what a subscription looks like. This is the work that I need to do as a front-end developer to consume the state change, right? I need to say that I'm subscribing to the order and I'm watching on the, and I want the ID, payment, and dispatch fields. This is the data that I want of this particular order, which has an ID 57, right? This is the work that I do as a front-end developer. That's it. I don't deal with WebSockets. I don't have to do with polling. All of that is taken care of by the GraphQL client. And I just have to specify this GraphQL subscription query, right? So this is what I have to do on the client. And this is the API call that I make over WebSockets to kind of subscribe to these events that are happening to the order ID 57 object, right? And this makes consuming async information on the front end very easy. So if you put all of this together, this is kind of what the stack looks like. We have a mobile web app that consumes a backend kind of thing with GraphQL using GraphQL queries, mutations, and subscriptions. And then you have some kind of event delivery system, which is kind of, and so you have to build the GraphQL API. That is a cost that we've now introduced in the system. Not only do we need an event delivery system, but we also need to build a GraphQL API that will support subscriptions. And so now you kind of have async serverless functions that do the rest of your business logic, right? The business logic that can be synchronous. And that's kind of the system that you're building. So you can either kind of, build this yourself, where you are, building the GraphQL API and the subscriptions part and, doing the eventing kind of system, and you can use the right tools for doing this, right? So you can use a combination. You can use a database. You can use something like you'll have to write a WebSocket server in Node.js. You'll have to have an event delivery system, maybe something like RabbitMQ or Redis or Postgres or Kafka or whatever. And then you will also write your serverless function in Node.js, right? So that's kind of what the high level what you have to do. Or of course, you can just use this cool open project called Hasura, which will give you the real-time GraphQL part and which will give you the serverless eventing, right? So that's also an option. Just saying. And so what I'll do is I'll show you a demo of what an application that is built in that style looks like, right? I just want to be clear that I'm using Hasura for doing the demo to show you what it looks like with Hasura, but the architectural concept that we have can be done, however you want to do it, right? This is just one way of doing it. So let me, and I think we can do, if you folks can see this URL, please head to this URL. And once you head there, just open up the order app, right? And I'll place an order and I'll show you how to place an order. And then, we can also, and we can look at the analytics as that order is placed. So this is a food delivery app. And let me, all right, cool. Okay, so I'm logging in as a user. And so this entire application is a sample application. This is a React app. This React app it's not using the entire backend is completely serverless. The state is stored inside a Postgres database running on RDS. The business logic is running with Lambda functions and Google Cloud functions, and and for the GraphQL layer, we're using Hasura, and I'll show you how that works in a bit. So what I can do is I can place an order, and I would like to have a donut and a mango, right? And I place this order, right? And now what's happening is that the order is going through some kind of process in the background, and it's kind of going through various states, right? So I have an analytics app that kind of shows, hey, this is kind of the order placed. These are the orders that are being placed in the system, right? And now if you notice, the app is blocked on payment, right? So let's make a payment here. This is a synchronous API call, right? Again, going to a serverless function, does the payment changes to restaurant approval state, changes to the delivery assignment state. And as those states change, you can see that happening on. So I think a few of you have tried this out but have not made your payments. And so now I can see that 3 users have not made a payment. So if you are on the screen, please go and hit the make payment button. And that way, we'll be, thank you. So cool. So now we're seeing that this backend is kind of changing states, right? So I have this UI, which is basically consuming this asynchronous information also and converting that to a graph, right? And this is again made easy because I'm using GraphQL subscriptions, right? So because I'm using GraphQL subscriptions, as you all are placing orders, and as those orders are changing the state in the backend, I am seeing that state change in the front end. And this was a very easy application to build because of GraphQL subscriptions, right? So let's take a look at how the backend was set up. So what we have on the backend is this is Hasura, which is the kind of GraphQL layer, and this is what these are what our tables look like on Postgres. So this is the most important table. So you have the order table, and these are like people who are placing the orders here, right? Recent orders that have kind of come in if I sort by created that. And these are the various states that are there in that order, right? So we have is validated, is paid, is approved, is agent assigned. Each order is linked to whatever order items have been ordered, just a standard kind of database modeling, nothing special here, right? And what Hasura does is that as soon as you create tables on your database, Hasura gives you GraphQL APIs that you can use to kind of start querying that information, right? So I can query for order. I can say that I need, I'm fetching just one order. I want the ID and I want the status of whether it's paid or not, right? So I can start, I have GraphQL APIs to kind of fetch that information, but I also have GraphQL APIs to kind of make a real-time query. And so these queries are now real-time. So if this information, if the orders change, then this information will kind of automatically change here. And I can go into that demo towards the end if you have time. So that's the GraphQL layer part of it. Now, the business logic that we have, which is for actually like doing the validation and for doing the delivery assignment, all of that logic is triggered via events, right? So Hasura has an event delivery system, and we say that, for example, if a new order is created, then we want to trigger the validate order event, right? And the validate order event is deployed on Google Cloud, where we have a serverless function which is running the validate order, right? And so we have, like, it has a default configuration of 100 retries with a retry interval of 10 seconds, and this is the payload that it gets, right? So every time there is a insert in the order table event happens, that event is put into a queue, and then that event is delivered to this function, right? And this function is stateless. So even if there's a network failure, if the user has placed an order and it has registered in the database, we have 100% guarantee that the validate order function will be called, right? And I'll show you a demo of that resiliency aspect in a little bit, right? So this is one part of the change, right? The next part of the change is that, okay, we want to do a restaurant approval. And so what that looks like is saying that, hey, if there is an update that happens on the is paid column, if there's an update operation that happens in the is paid column, deliver the event to this AWS serverless function, right? And I've just used different serverless functions deployed to different cloud vendors just to show that it doesn't matter where code runs. And that's the next event that runs, right? And similarly, we have the delivery assignment function, and that kind of runs here, where we're saying if there's an update to the where the restaurant approval has happened, the next event will be triggered and delivered to this particular serverless function. So that's the configuration of doing the real-time GraphQL and the eventing that Hasura gives you. And if you were setting the system up yourself, that's the layer that you would have to build yourself. But the rest of your business logic inside your Node.js functions deployed to serverless remains exactly the same as it does, right? You take the order object, you figure out if it's valid or not. You take the order object, you figure out if it's paid or not, and stuff like that. So great to see that there have been quite a few orders that you folks have placed, right? And if you look at this particular graph that I've built, right? This particular graph that I've built was also super easy to build, because all I did was, I ran a subscription to say, how many orders are validated, right? So I have to keep a track of how many orders are validated, and this is a real-time kind of thing, and this number will keep changing if the order validations change, right? And I set this up by creating a view in Postgres saying that, I would like to keep track of, I want to keep account of the order table where is validated is true. So as soon as I create this view, I can create a subscription to it, and I have a subscription that tells me, how many orders are validated. I use this subscription to easily build this UI, which kind of now shows me, what is happening with the orders that are being placed. So building this graph in real time and whatnot is super easy, right? If you have a real-time GraphQL layer. So that is one aspect of showing you like how the application is kind of put together. Let me move to the next aspect of showing you what resiliency looks like. And I have a recorded demo for this so that it's kind of easier to look at. So let me just hit play on this YouTube video that I have. I apologize. I think something is wrong with my internet, but let's just give this a few seconds to kind of load. All right. So just like what we're placing orders, and this was a modified version of UI where we were placing 1,000 orders, right, at a time. So in one shot, we placed 1,000 orders. That means suddenly we'll have 1,000 different payment processes, 1,000 different restaurant approval processes. The first, so you can see that the validation function is running, and we have 1,000 different validation functions running. And as they are running, we can see that the status is like, we can see that our graph is getting updated. So we created 1,000 orders. Those 1,000 orders got validated. Now we're waiting for the users to finish the payment, right? And as soon as you do the payment, you can see that and if you look at the right portion of the graph, you can see the payment has happened, and now the payment functions will start kicking in, right? So this is a normal scenario. We know that if we have order validation and order payment, these things will work, right? What we're going to do now is we're going to simulate a failure, right? So let's imagine that there is a network failure. Let's imagine that between our event system, which in this case is Hasura, between our event system and our serverless function, there was a network error where our event system could not contact the serverless vendor and could not make the API call. So what we'll do for this is we'll go to the AWS gateway and we'll set up a throttle. So what we're going to do is we're going to throttle this. So you'll look at the serverless functions that are running, and suddenly you'll see that the serverless functions are flattening out, right? And what you're seeing here is that we've taken a particular serverless, we've taken this restaurant approval kind of, one of the serverless functions, and we've throttled it. So that particular function has failed, right? And because it has failed, all of the orders have gotten processed till that stage, and they're not able to move forward because there's a network error, right? And so now imagine that there is full panic, everybody's panicking, and the users are all stuck on approval, and we're all panicking about what to do. So then we contact our developers and we say, hey, fix this network error, do something. And they fix the network error. And that's what we're doing now. I'm just simulating a fixing of the network error, which is basically we're removing the AWS throttle. And as soon as that, let's say that network connectivity is fixed, things just pick up exactly from where they left off, right? It doesn't matter. It doesn't matter if there was a disaster situation. We had to, replicate the entire database, move it to a different environment. We had to switch the DNS. Nothing matters, because as soon as the kind of connectivity is restored, events get redelivered. And as soon as events get redelivered, we know that the processing will ultimately complete, right? So that's kind of what, that's the ease with which the system that we built was automatically resilient, right? And that's kind of the resilient nature of this particular application. So so that's kind of what this looks like. And if you folks have questions, please feel free to ask questions. Please do check out the open source project that we have at Hasura, and where it gives you the real-time GraphQL layer and serverless eventing. We're a young project. We just launched this a few months ago, and whatever feedback you have will be super relevant for us. Please do try it out. We have several large users in production also. So it would be great to hear from you. We have a very active Discord community also, where we're talking about this style of building applications, which is the three-factor architecture of building scalable and resilient systems with servers and GraphQL. So feel free to hit us up there as well. But otherwise, if you folks have questions, I can take questions now. If you can see my face.
Hi, let's wait if someone writes some question here. I think no questions, maybe.
That's awesome. That's a perfect presentation then, or a really bad presentation. One of the two. I'm going to hope it was a good presentation.
yes. Really good, really good.
But I'm online on Twitter and stuff. And so if you guys have any questions, you want to reach out, feel free. And I'll post a link to these slides on the meetup group also, so that you can check it out.
There was one, he asked if you will share the presentation.
Right.
If you have the GitHub or something else, or you
I will definitely do that.
I will post it in the meetup. So
I'll do that.
Yes, okay. Then let's send me the presentation and I will upload it to the meetup. Okay. Fine.
Absolutely, absolutely. I'll do that.
And I think nothing more. So thank you, Tanmay.
All right, that's awesome.
Great.
Fine.
Bye.
Thank you for having me.
Bye.
Bye. Bye.